And I'm the author of Machine Learning with TensorFlow 2nd edition. My name's Chris Mattmann. I'm the Deputy Chief Technology Officer at NASA's Jet Propulsion Laboratory. I lead the innovation team there. Everybody that works for me does machine learning. It's kind of intimidating at some level, but additionally, it's something that is really inspiring too. People are using machine learning from everything at NASA JPL to mine and look at data now related to things like COVID, mining publications, trying to figure out treatments and diseases and things like that, all the way to looking at our clean rooms where we build the flight hardware that's on its way to Mars, like our next generation Mars rover, which is called Perseverance. We're using machine learning to basically capture data in the clean room there, particulate data, to make sure that we don't contaminate the hardware that we're going to put basically on a rocket and fly to places like Mars and other places in the universe. We capture that data, we upload it to the cloud, and then we try and make predictions about whether or not we've contaminated the hardware. And we use things like TensorFlow, like we use in my book, and I'll talk about. TensorFlow is a modern machine learning toolkit originally started by Google. We're doing that. Maybe go through a couple of more examples real quick of some of the things that we're doing at JPL that's pretty cool. Another thing that we're doing, it's also Mars rover related. Today, all of our space and flight hardware uses a very old processor, like an iPhone 1 processor called the RAD 750. And the reason that they do that is it basically it needs to be what we call radiation hardened hardware that goes up, because when it gets up into space, there's cosmic radiation and it can do all sorts of crazy stuff, the least of which is simple things like flipping the bits, the ones and the zeros opposite, which can screw things up totally. So most of the hardware that we fly, nearly all of the hardware that we fly, is what we call radiation hardened, which means we've tested it, we've made sure that it can withstand cosmic radiation. And so related to that, because of that, it's sort of made us a little bit of behind the curve in a way for getting, I would say, the type of hardware you expect on your laptop or terrestrially and things like that. GPUs, big computing to do deep learning, machine learning, and other things. But tomorrow, we'll have that. We'll have things like a chip called the High Performance Spaceflight Computer, which will be a GPU-like radiation-hardened chip. Or we'll have things like Qualcomm Snapdragon, which is going to run on our Mars helicopter, which is pretty awesome as a technology demonstration. So in these environments where tomorrow we'll have actual computing power to do machine learning, like what could we do? So some of the things my team is doing at JPL is envisioning sort of what are the killer apps that they could use in those environments. And so a couple of them are, we use about 200 images a day to get back from Mars. It's because it's about an 8-minute sort of round trip flight time from Earth to Mars to send a message and get a response back. So we use about 200 images a day to plan what to do the next day on the surface of Mars with our existing rover there, Mars Curiosity, or MSL, Mars Science Lab. But tomorrow, what we'd like to do is run deep learning on the rover itself with one of those newfangled CPUs like I talked about. Use one of those high-performance spaceflight computing or Qualcomm Snapdragon type of chips and run a machine learning model on board. And tomorrow, get back 1 million captions, right? Because text is cheaper to send back than images and things like that. And if we could run machine learning and deep learning on the rover, caption what it sees, we could get back millions of captions rather than hundreds of images, and then have something really cool and a lot more information to do planning for the next day of rover operations. So given that, those are just some of the cool things that we're doing with TensorFlow. And, sort of besides that, one of the things I wanted to talk about, here is my book. And so how did I get started in machine learning, and, what types of problems are machine learning technology sort of best suited for? So, like I said, my team, we're the innovation team at JPL. And basically what we do is we work on very hard problems, like I was just talking about, like, figuring out how to use machine learning for the next generation of Mars rovers, or decontaminating our clean rooms where we're sending flight hardware and things like that. So, you know, in those environments, how are we using machine learning? Well, we're doing things like making predictions. We're classifying things. We're classifying images. We're, looking at an image and generating the text for it. Those are some of the things. So those are some of the awesome things that you could actually use TensorFlow and machine learning toolkits to kind of take care of. So how did I get started with TensorFlow, and why do you care about it here in the book? Basically, what happened is my team has been using TensorFlow and other machine learning toolkits for a long time, for the past few years. And I'm a classically trained sort of statistical person. I didn't know a ton about machine learning and deep learning 2 years ago. And as a former Manning author, I wrote about 10 years ago the book Tika in Action. Basically, as a former Manning author, I get Manning books. And so I either browse them or peruse them or grab them. And I saw the first edition of Machine Learning with TensorFlow that was written by Nishant Shukla, who's a recent graduate in 2017 of UCLA's PhD program in computer vision. And I was reading the book, and it was really amazing. I mean, I like to learn practically and using applied knowledge. And basically, there was tons of examples in the book, tons of just here's how you take the code and use it. Very practical, very easy to pick up. And so I started kind of working my way through it. There was a chapter on regression. There was a chapter on classification. There are chapters, in the book about how to do convolutional neural networks and machine learning and things like that. So besides that, as I got started kind of going through the book, one of the things that kind of hit me hard, Nishant had this habit of, at the end of a chapter, putting in the bullets kind of at the end. Oh, by the way, yeah, I just taught you about regression. Why don't you download this data from New York's 311 call center, which has a bunch of their call data, and why don't you make predictions about, their monthly call cycles and how many calls they're going to get next month and things like that. Okay, so that seems kind of easy until you get started. And what happens when you get started is you realize there's a lot of data preparation, a lot of cleanup, a lot of downloading, and just getting the data what we call analysis ready or machine learning ready. And that really wasn't covered. And I teach at USC. I'm a computer science professor there. I teach graduate courses in big data and search engines. And I'm sitting there 5 weeks later, and my wife's asking me, hey, why are you staying up so late at night? And I'm like, I see the future. It's machine learning, and I'm doing it. And so I spent about 9-10 months going through the book and really, really taking my time with all of the, quote, suggested examples at the end of it. And what happened was, about, a year later, I had a whole new book, basically. I had a whole new book. I had tons of Jupyter notebooks. I had a GitHub repository. I had these very in-depth notebooks where I took a bunch of notes and walked through all of the data preparation steps that you need for machine learning, with TensorFlow. And basically, that's how the second book was born. That's how the second edition was born. I'm adding about 9 to 10 new chapters. Each one of those new chapters is basically, where a suggestion was made in the first edition of the book. And then I actually took the time to do that suggestion and walk you through the machine learning, the data preparation, the cleaning, and everything that was necessary to do that. So, the book kind of starts out with traditional machine learning. It doesn't jump right into deep learning, convolutional neural networks, and things like that. It goes and teaches you models like regression, which is basically how to make predictions with continuous numbers and data, not labels or things like that, but how to take a bunch of continuous numbers and then predict the next set of continuous numbers. That's basically what regression is. It goes through classification, which is getting a set of data that has labels associated with it, and then trying to predict labels of unseen data based on what you've seen before. That's classification. After that, it takes you through some other unsupervised techniques like clustering, which is a pretty cool technique, which basically looks at data and then tries to group it together just like anyone would. I got 3 kids at home. I'm constantly cleaning up after them. I'm constantly, I got 2 that are under 5, and they love to just go from room to room and make mess, especially during this time. And what do you do when you do that? You take, items and you sort them together, based on what seems to be the relationships between them. That's unsupervised clustering. We take you through that in the book. The same approach and process works for data as well. After that, in the book, we go through hidden Markov models or probabilistic models. Basically these are making predictions, trying to predict the internal state when you can't directly observe it. It's kind of like trying to predict whether you should go out walking when really you want to know what's the weather going to be like. And we all know how hard that is to predict. So that's kind of a classic example of what we call hidden Markov modeling. And guess what? TensorFlow, this great toolkit from Google, this great framework to do machine learning, it doesn't only do deep learning and machine learning. Although you may hear about deep learning and machine learning today as sort of the only machine learning, we'll talk about it in a sec, but there's lots of other machine learning, and it's actually a little bit better because these models like classification, regression, hidden Markov models, things like that, probabilistic models, they're all explainable. You can explain to someone why the model made a decision that it did. Whereas it's a lot harder to do that with deep learning and neural networks, and no one really tells you that. So basically, that's kind of the first 2/3 of the book. Is it walks you through, basic, getting started with TensorFlow, understanding basically what machine learning is, walking you through explainable models, and each one of those intermediate models that it introduces, I add a new chapter where I show you, okay, we've taught the theory, and now we're going to go into an actual example of it. And it's not just sort of an afterthought in terms of a bullet where we kind of mention, hey, try this. We walk you through 20 pages or 30 pages of how to do it with a Jupyter notebook and things like that. So I'm just going to pause real quick because I see there's a ton of questions and comments, which is awesome. So let's see. What do we got here? People are talking about regression, winning the lottery. Yeah, absolutely. Right, making predictions. Can you look at regression and make predictions on numbers with lots and lots of data? And if the features are discernible and modelable, and if there aren't any hidden features, wouldn't that be nice? But unfortunately, winning the lottery, can't even talk. I wish I could win the lottery. Winning the lottery has a lot of unmeasurable things which have to do with randomness and prediction, and probably, if you think about it, the features of those balls as they come down the machines and things like that. So I suppose if you could actually model the machine that spits out the balls and all of its perfections and imperfections using a number of features and regressions, you might have a shot at that. But thanks, Dowser TV, for the question. Let me see some of the other questions that are coming through here in the chat. Awesome. Yep. Great. So what else do we got here? Just looking through some of the questions. Lots of cool emojis. I'm going to have to get my emoji game up on this. So keep the emojis coming. All right. So, some of the other questions that came as we kind of collected these over the week. How am I using TensorFlow professionally? So I'll get back to talking about the book and things like that and telling you all the awesome new content and stuff that we're doing. How am I using TensorFlow professionally? So, it might surprise you. A lot of the people on my team, the innovation team at JPL, they actually don't use TensorFlow. And, I attribute it, it's this funny thing, I have a lot of innovators that do what I call technology chasing. And to me, basically the analogy is you could always sort of try and, buy the next sort of weapon and things like that, and try and constantly learn how to use that weapon well. Or you could have a few weapons, maybe one, and know how to use it really well. And that's the analogy to me. And so my whole career, my 20-year plus career at JPL, industry, open source, and places like that, academia, I've usually been the person that likes to learn how to use a weapon pretty well, one of them, so I don't constantly chase down other tech and things like that. It's not a bad thing. We need people and innovators that do that, but I'm the type of person that's usually, a little bit behind on chasing the brand newest thing and things like that. Amazingly, TensorFlow just keeps innovating and having new things, but I actually got started on the first version of it, maybe around the 1.0 version of TensorFlow, and now my primary version that I use is either the 114 or the 115 branch. And so people ask me, why do you use that branch? And why aren't you using, the latest TensorFlow 2x and integrated with Keras? It's awesome, actually. It's got tons of new features. They've got tons of docs. All the docs on the TensorFlow site have been updated to that. Most of it, a lot of it is backwards compatible with 1.14 or 1.15. What I do is I do a lot of work on big supercomputers. A lot of the machine learning we talk about in the book that I mentioned. And this was something that didn't come through in the first version of the book, so I don't hide it from you in this version. Is that when you click train on one of these models, when you're doing machine learning and you click train on one of these models, you're going to wait for hours, days, sometimes in a week when you get to the facial identification and building a convolutional neural network chapter. You're going to wait a while. And so the big challenge, with that is that I tend to use machine learning images and Dockers and things that have already been built that are running on big supercomputers. And I do a lot of work with big universities that run big supercomputers that aren't, say, Google's of the world, but maybe that provide, 100 nodes, with a bunch of NVIDIA GPUs or things like that in them. And you'll find if you go to big research institutions that when you do that, a lot of them are still running the 1.14 or 1.15 stable branch. They haven't done it, and it's because there's so much code and software that's already been written in those branches, and there's just enough nuance in terms of the upgrades to 2.x and things where it's not a one-to-one direct mapping, that because of that, you are tempted and you're wanting to kind of keep your code and heritage on the 1x series and to run them on those big supercomputers where they're still running it. A lot of people ask me that. A lot of people ask me, oh, Chris, why not 2? Why not all this? And I tell them I work with the people at Google, and Google will be maintaining the 1.x TensorFlow for the next 3 to 5 years because it's that sort of ingrained in companies and things like that. And it's not a one-to-one mapping. They're not going to just throw it all out right away. There's so much technical debt there that, and there's still amazing things that you can do with it. And so the book covers as its primary sort of technology lingua franca 1.14.1. I am planning in the appendix to go through at least one of the examples of the chapters in the book and show you how to port it to TensorFlow 2, just to give somebody a recipe for how to do it. If you think about machine learning, 80% of the work is data cleansing, using things like Pandas, NumPy, numerical Python, Matplotlib, Jupyter, and things like that. All of that code works the same, whether you're using TensorFlow 1 or TensorFlow 2. The big difference is really in setting up networks and higher level APIs. And integration with things like Keras and things, which were a major part of TensorFlow 2. I'll talk a little bit more about that later. I got a question that popped up from Ralph. So Ralph, you're talking about debates about people talking about deep learning where they talk about shallow learning will do. Your point is that deep learning can figure out the feature engineering on its own and discern features in data, and isn't that a good thing? Shouldn't it be the first go-to without using so-called shallow learning or explainable models? So that's a great question, Ralph. Basically, my take on it is this. If it's an image or computer vision problem, deep learning outperforms regression, classification, or any of the traditional techniques by an order of magnitude mostly. So depending on the data and the domain, if it's computer vision, I might jump straight to it. I might jump straight to deep learning or deep learning, for that. Because, I'm going to want to use, if I'm doing labeling, I'm going to want to use something like Inception or ResNet 50, or I'm going to want to use sort of a model, that really, really gets state-of-the-art results. And really neural networks and deep learning are where that's at for, image problems. The challenge that they have right there, Ralph, and the big challenge that I'll tell you is that as soon as someone asks you, why did it label? Why did it give the label for the image? And so let's take an example real quick. Let's talk about where you're not just asking sort of the deep learning network, and let's say you built it with TensorFlow, so you're using Inception v4. You're not just asking it to make a prediction on an image of a cat, or maybe your favorite football player or team, or things like that. I'm a USC fan myself. Fight on, go Trojans, Southern California, LA right here. Let's say you're actually giving, the neural network and the computer vision network let's say you're giving it a picture of sand dunes on Mars or dust storms on Mars. The challenge that is going to happen there is it's going to label it wrong. And so an approach that we use to solve that nowadays is what we call transfer learning. And that's basically where we keep the same network that we use. We don't redo all of the investment that was made in ImageNet or in Inception and things like that. But we chop off the last sort of head of the network that gives, or the outputs of the labels. And maybe it looks at a sand dune on Mars and it thinks it's an elephant, right? Because that's the knowledge or the terminology terrestrially that these machine learning models have been built off of. We want it to recognize that. We want it to recognize that, but what we want it to do is to give it our labels. So we do what's called transfer learning. We give it a new set of labels to every time, it sees what it thinks is an elephant. We're giving it those Mars sand dune pictures. We actually wanted to call it a Mars sand dune. That's one way to kind of leverage the existing investment in deep learning and in these models and things like that. But the challenge is, as soon as you need to explain it to somebody, as soon as you need to explain where that label came from, it's actually really difficult because you've got no clue. Say you're using AlexNet or Inception or any one of these very popular computer vision models. If you just tell people, I used the fully connected 7 layer, or I used the pool 5 layer, and here are the features for it. The challenge is that's just a bunch of neurons or numbers that are turned on or off, or that have learned a particular compact value. And that's really hard to explain. It's really hard to explain what those neurons are actually capturing. So explainability is a big deal, right now. And so that's the challenge, Ralph, is that that's the only reason. So what I see a lot of people doing nowadays is, even in those domains, you start out with deep learning, get the really state-of-the-art result, get the label, and then go back and use some of those shallow type of learning like you're talking about to perform explainability. Here's why I got the labels. Or you use transfer learning, right, for methodologies for that. Great question. I'm going to go through some of the other questions that I've got here. What are some of the prerequisites for working with a library like TensorFlow? Should I have a comprehensive understanding of the math, or is it involved enough just to know the results of a given function? So that's a great question. So some of the prerequisites, so whenever you're doing TensorFlow nowadays, we're using 1 or 2, it doesn't matter. I guarantee you're going to want TensorFlow and friends. You're going to want Jupyter, which are basically IPython notebooks. It's called Jupyter Hub. It's basically interactive notebooks where you're doing data science, you're putting Python, and let's just put it out there. I'm a guy, I helped invent Hadoop and most of the Java ecosystem for big data. So I'm not renouncing Java, but I can tell you that data science is Python nowadays. So you're doing Python, and it's just sort of the lingua franca. You're doing Python, and you're doing it in a Jupyter notebook. You're in Jupyter, you're interactively putting Python code into the cells, you're interpreting it, and so forth. You're looking interactively at the data in NumPy or numerical Python arrays. That's another TensorFlow and friend, NumPy. It's basically the matrix or n-dimensional array library for Python. Performs amazing operations like slicing. It's basically what we call, it's the library that tensors are built off of. So basically, tensors are matrices that you take and that represent, basically, they model kind of the way that our brain is. So our brain is a set of neurons that are interconnected in different ways, right? Neurons basically fire or they don't fire. Our cells transmit electrical pulses between the neurons. That's how they're connected. And that's how our brain basically models things and makes decisions. Tensors are the computer representation of neurons, and tensors are basically, fired functions, whether they're on or off, or a 1 or a 0, and they're connected in a particular way, which we call a neural architecture. So NumPy is the underlying library to model tensors in Python. So NumPy is your friend. It's what you're going to use to create n-dimensional matrices to represent both classes of objects, input data, features, things like that. Again, Jupyter is where you're writing the Python code for that. Additionally, you need things like Matplotlib. Matplotlib is the library which you're going to take a look at your input data. I give you a bunch of images, right? And you want to basically prepare it for machine learning. One of the things you might do is, if those are red, green, blue images, RGB, 3-channel images, you might want to convert them to grayscale, right? you might want to take the RGB channel values and reduce the number of features or the number of pixels that you need to learn. And one way you could do that is you could average the RGB pixels. You could take a 124 by 124 image or a 244 by 244 image, whatever, width by height. That's the amount of pixels that you want to learn. In an RGB image, that's a basically rank 3 tensor because it's got 3 basically dimensions on that. It's got X, Y, Z for that you have to learn. Why not change it into a one-dimensional tensor? One way you could do it is do it in grayscale, right? So you put it in grayscale, you average the RGB values for the image, and then you might want to take a look, hey, did this work? This is, when I was writing my first sort of convolutional neural network, when I was putting the material together for the book, and I was doing a facial recognition system, you want to be able to tell, hey, did this grayscale work? I'm looking at a bunch of celebrity images, like we take you in the book. In the later chapter of the book, when we're doing convolutional neural networks, I basically show you how to build a facial recognition system with high accuracy based on this labeled celebrity data set called VGG from the Visual Geometry Group at Oxford. One of the things that you want to do when you're building notebooks for that is just, again, if you're converting those images to grayscale to reduce the dimensionality, to make it easier to learn, reduce the amount of parameters that you have to learn, you might want to check it. And so the way you do it is with Matplotlib. You can use Matplotlib to visualize properties about data. So that's another TensorFlow and Friends. And then there's various other like image reading libraries. sklearn provides image reading libraries and image display libraries. OpenCV for computer vision and for displaying images and things like that is another library. So these are all the things that really, if you're doing data science, if you're doing machine learning, if you're using TensorFlow nowadays, you may spend 80% of your time putting together all of the preparatory work, for this. You may spend 80% of your time putting together all the preparatory work where you never even are using TensorFlow, using all TensorFlow and Friends. You're using, things like OpenCV to manipulate the image, to reduce the dimensionality of it, maybe to view it. You're using Matplotlib to plot some statistics about the images. You're using NumPy to represent the underlying matrices, those 244 by 244 by 1 matrices. NumPy is really the tensor backend library for that, to capture the ones and the zeros. So those are all the things. So people ask me, oh, you're doing TensorFlow, is that all I need to know? No, you need to know TensorFlow and Friends. And the book totally covers that. We cover TensorFlow and Friends, we cover all those ancillary libraries and so on and so forth, for that. So let's see, what are the prerequisites for working with a library like TensorFlow? Should I have a comprehensive understanding of the math involved? So, basically in terms of understanding the math, just that second part of the question, I'll tell you, I was really good for a while at math. I would say I was good in high school. I was good my first couple years of college, but I wouldn't call myself a mathematician by any means. And it's certainly, a couple years ago when I started down this path had been, a while, maybe five to 10 years before I was really hardcore into math or using it day to day. Anything beyond just, I would say, traditional algebra and, modeling word problems and things like that. I had done some geospatial work where you kind of needed a little bit of algebra and geometry and things like that, but I wouldn't say it was hardcore. Really, in order to understand tensors, I think anybody could do it. I think anyone could understand, and you use tensors, by the way, not just in neural networks, but even if you're doing classification, even if you're doing regression, there's still the notion of matrices, of setting up basically input features of data, where the rows are the items of data and the columns are the input features. Those are matrices. And then trying to learn either the weights or the parameters that turn that input features or data into the labels that you want. So really, all of this becomes trying to model a system of linear equations. That, I would say, is probably a prerequisite. It's not something you can kind of skimp over and just ignore. That said, it's not the hardest thing to do in the world either, right? If you can figure out how to multiply numbers or how to set up matrix multiplications, and it doesn't have to be super complex, 32-dimensional matrix multiplications to start. If you can just multiply variables and matrices, one by one, you can do TensorFlow, you can do machine learning and deep learning, and I'm evidence of that in the book. So let's see what else. Is your book suitable for somebody totally new to programming, for a comfortable programmer that wants to move towards machine learning research, or do I need to have some familiarity with both before picking up your book? So, is my book suitable to someone totally new to programming? I would say, so I was trained as a software architect, software engineer. I spent a lot of time trying to think up how to build, design, I would say, reusable code. My work in open source, I think, is evidence of that, and so on and so forth. You can, many, I would say tens to thousands to hundreds of thousands to millions of people really use the code that I wrote. The book is really an extension of that. I don't think you need to be an expert programmer in Python to use the book, but I think you need to have some skills with a number of these sort of concepts or libraries. If you don't know Matplotlib, that's okay, but you have to understand something about visualizing numbers, okay? If you don't know NumPy, but you kind of can learn about, multiplying numbers and matrices and things like that, well, then you can do the book. If you have never worked with text before, you should play around with text. If you haven't worked with images before, you should know something about, how to display an image or look at the pixels or get the pixel values for that. Besides that, what I'll say is the book is very, very well annotated, and Manning does a great job at this. This is why, I'm so happy to be, a Manning author. I'm so happy to be working with Manning again. And I just love, Manning, and you might think I'm a homer, but I'm not. I'm a real big fan of the way they teach. And look, I've taught some of the best people that are running Silicon Valley companies nowadays, and I can tell you, it's not always those deep, 700 pages, heavily mathematical books that students learn from. And so I would just say, if you get the book, you pick up the book here, Machine Learning with TensorFlow 2nd edition, you will see there are a number of annotations on all the code listings. So I've tried as best as I can where, you might not have had some particular experience in one of those libraries with TensorFlow and friends or things, to basically tell you what it's doing in simple terminology and simple language. And the other thing I would say is that nobody's perfect, and but the analogy to that is that, I've also thought a lot about how to have communities of software sort of have those people stand on their own and learn and stand on their own. And I would say that there's sufficient, examples in the book. And really this 2nd edition is the book you need to do this, because it's got the actual real world examples. It's got the in-depth, not the ones that you can cover in 5 pages that illustrate a theory. I'm talking brand new 30 to 40 page chapters that say, oh, you want to do classification? Let me download the entire Netflix IMDb data set on movies. Let's ingest it, and let's learn the positive and negative sentiment reviews from it so that you can have your own positive and negative sentiment classification and predictor, right? Oh, you want to, do hidden Markov models and so forth? We won't just do the one off Wikipedia that's the, I want to do rainy or sunny and decide whether I should go walking or clean or do things like that. That's the very simple one. Basically, what I show you is use hidden Markov models to parse all of the Brown corpora, which are all of these textbooks that are part of the Gutenberg project. Parse and learn all these textbooks, have the AI and the machine learning basically learn parts of speech, learn what's a noun, what's a verb, things like that, and then use hidden Markov models to predict on unseen text what are nouns, what are verbs, what are adjectives and things like that automatically. So what I'll say is that the book progressively builds you up from kind of simple examples and theory into very in-depth, what I would call graduate school level challenges or assignments. And it spends a lot of detail kind of taking you through everything that you need to know to basically implement those. And, I don't shy away from basically telling you, when you click train here, you're going to wait 2 days if you're running this on a laptop. Or you might want to go to the cloud for this, right? Because the funny part was when I did the 1st edition of the book, that was all learning on my own. That was all stuff I had to learn on my own, right? Nobody told me that. So I'll save you the trouble there and walk you through that sort of on the book. And that's what I'm doing. That's what I'm doing here, in the 2nd edition of the book, is I'm going to walk you from the basic code listings and the basic examples. I'm going to walk you through the whole thing I'm going to walk you through to the point of where you can implement this stuff in the real world, and where you should know enough about it that you'll be able to stand on your own, use it in your job, and things like that. Let's see. So, okay, before I get to one of the ahead of time sent questions, Ralph has another question. You're asking, does the book have any examples of using a model from TensorFlow Hub for a project? New deep learning students would do projects with existing models instead of long training of your own. Yeah, so that's a great question. So some of the existing models, when we get to the deep speech, so later on in the book, one of the near to the end chapters, we go over recurrent neural networks, and then we talk about LSTMs, long short-term memory. What these are neural networks that model in the brain sort of how we have memory based on time series, points in time, where we remember things, and our brains are sort of hardened with memories by seeing data points in time over and over again. And LSTMs and RNNs model the flow of information in our minds and the learning over time. And so one of the really powerful things that LSTMs and RNNs have been used for, just in general in machine learning, is for a lot of speech recognition, because you can imagine time series data related to that, getting audio files and transcripts and so forth over time, and then doing using basically LSTMs to do what we call bidirectional LSTMs, or learning character by character when we've seen certain characters in words, predicting what the next words are, or when we've seen certain audio signals and things like that, predicting what characters they're actually associated with. So when we get to those LSTM RNN portions of the book, there is some leveraging of models that are from TensorFlow Hub. Basically models related to the LibreVox corpus and deep speech and so forth related to that. There is some leveraging of models, but I don't want to hide it from you. And I would actually say, in my own experience, you will end up training maybe not the most robust, accurate, most reused model in some of the generic areas like speech recognition or image recognition or video recognition, but there is such a market right now, and I tell people this when they ask me, like, what's the hot market in machine learning or automation or using TensorFlow and things, and I said, it's training domain-specific models. It's training models of shipping and supply chain things. Hey, you want to make a machine learning model today that will really sell, that you should train on your own because Google might not have access to the data or the local things going on, for you. Try and build a predictive model for supply chain of materials related to COVID, PPE, or personal protective equipment. Because I can tell you, there's no centralized company or existing model that knows really well how to model the supply chain for that, or how to make predictions or classifications, or to look at a set of deaths or cases and make a regression and make predictions on that. So I actually think you will end up training a lot more models than you think you will. There's going to be a lot of reuse. I mean, certainly you may never go back and train, say, an ImageNet or something like that. You're going to want to reuse those, but you're going to be doing a lot of training, I think, too. And so, yes, anyways, the book covers both. The book will cover TensorFlow Hub, and, especially in some of the later chapters, and getting and reusing some models from that. Additionally, the book will teach you how to build both medium and complex models of your own, for cases like that. So that was a great question. Thanks, Ralph. And then what do we got here? Looks like Deza, what is the easiest way to start using TensorFlow? I remember not being able to run it on Windows 10. That was a little while ago. Things might be different now. Hey, trust me. The Windows to Linux bridge with a lot of these software, you're talking to somebody, again, who helped create Hadoop. I can tell you, we always used to tell people, hey, download and run Hadoop. And then, it took, the team that was working on it and Yahoo and a bunch of other companies, like, years after delivering the 1.0 release to actually get a good Windows build. So I feel for you. I apologize. One thing I can tell you on TensorFlow, even on Windows, it does run on Windows. The easiest way to get it up and running is with Docker, in my opinion. And we do cover that in the book. Standing it up with Docker, getting even on Windows into a Linux environment with Docker, and then having the Docker, just install it with pip. pip install TensorFlow on Linux, Unix, Mac, and things like that work very well. Nowadays there's not a big problem, and on Windows, the biggest advice that I have is to use Docker to do it. So thanks for your question, Deza, and we do cover that in the book. Ryan, you asked, does the book contrast TensorFlow with other frameworks like Pytorch and contrast using raw TensorFlow with using the Keras API? Great question. So I don't spend a lot of time contrasting it with Pytorch. Anecdotally in the first chapter or so forth, I note some of the similarities and differences, between TensorFlow and Pytorch in that. But I don't spend a great deal of detail doing it. I think there's a lot of books already, on things like Pytorch that cover it well, I would say. I just didn't want to kind of go into that, I would say, in the book, and I'm mostly focused on TensorFlow for that. The element about Keras, I don't directly go into Keras in the book because I don't directly cover TensorFlow 2, but I am planning, again, in the appendix on taking some of the examples that are in the book, at least one of the examples, like the more detailed ones, like either the call center regression and or one of the classification problems, and then just showing you how to port it to TensorFlow 2. And when I do that, I will use Keras for the layers and stuff for that and show that conversion. So that will be covered there. So thank you. These are great questions. Excellent. So, all right. I think I covered all the questions there in the chat. So finally, why should I pick up your book? And after reading your book, what should I do next? So basically, here's my pitch to pick up the book. I was somebody who I'm a PhD computer scientist. I'm fairly well accomplished. I'm the deputy CTO at NASA JPL. But 2 years ago, I didn't know anything about machine learning. I picked up the first version of this book, and I wouldn't call myself a Python expert when I did it. I wouldn't say I knew everything about Python and Friends, all of the tools that I'm talking about, things like that. And within about 9 to 10, 11, 12 months, I had a full set of Jupyter notebooks, a set of big plans for how to use machine learning everywhere, and I knew TensorFlow and machine learning really damned well. And there were all these notes that I had about how the book could be improved with examples, how those examples could turn into new chapters, how we could provide so much more detail, and information. And the second edition of the book is that. The second edition of the book is basically, here's how you don't have to take 11 or 12 months and to learn all this stuff. I can get it down to hopefully, in 3 months, maybe a fraction of that time. Maybe that's how long it'll take you to get through the book. It's certainly a couple hundred pages longer than the first book. But those couple hundred pages are a ton of detail, a ton of executable code that works. I ran into a lot of issues in the first edition of the book because it used an even older version of TensorFlow library, the 1.0 version. Everything works, everything, I won't say compiles because Python's an interpreted language, but everything runs without error. All of those Jupyter notebooks that I'm making available in GitHub all run. And again, this will show you everything from reusing a model and just applying it nowadays to basically building your own model, right? And modeling problems that you see in the real world. If you work in a call center, if you work in natural language processing and text, if you work with imagery, videos and things like that, if you work with speech and sound, those are all the major areas. And I walk you through it in the book. And, that's why you should pick the book up. That's why that's the simple reason is that it's a comprehensive, complete introduction to not just machine learning, not just TensorFlow, but the whole gamut, and TensorFlow and Friends, and all of those things. So thanks for that question. Let's see. Okay. I'll tell you what, I think that's all the questions that were submitted. Okay. And it doesn't look like there's any more questions here in the chat. I'll pause for a second and just see if anything pops up. Hey there, Slims. Do you have a question that I can answer? Okay. So it looks like we're wrapping up here. It looks like there's no more questions. Hey, I wanna thank everybody for tuning in. I want to apologize for the technical difficulties that I had, getting started. I'm a new Twitcher. My son plays Fortnite all the time. I should be a pro at this in a few months, especially if we're quarantined for longer. Hey, I want you guys all to have a great time. Thank you so much for joining me. All right, let me answer this from Coop real quick. Coop56, you're an experienced software engineer but fairly new to AI ML. Would this be a good book for me, or is it more focused on beginner programmers? Coop, that was me, brother. I was, as experienced a software engineer as you can be, basically. And that was me, new to AI and to ML. I would say statistician and search engine, statistical information retrieval by training, but not AI and ML. And basically this book, Machine Learning with TensorFlow 2nd edition, is tuned for exactly that profile. You're exactly, what we call our qualified reader, for that. So yes, it's not too, I would say, beginner. It involves fairly complex and fairly detailed, examples. I've added about 9 to 10 chapters of really real-world examples of how to use AI, machine learning, and TensorFlow in real-world situations with lots of different types of data: text, sound, audio, imagery, video, things like that. So please, would love for you to pick up a copy, Coop, and thanks for your question. All right, so given that, I think with Coop's last question and with no more questions on the list to get submitted, I'm going to go ahead and sign off. Thanks to everybody for listening. I really appreciate it, and take care.